as well as the ATLAS experiment at LHC. And I don't know if you realize this, but this is being a physics coordinator at ATLAS at LHC, where there's 3,000 collaborators to manage all of the physics output, is actually one of the great challenges in the physics world, I believe. So for the last couple of years, he's been helping DOE manage the LHC program, and he's going to talk to us about what happens when you build the world's largest microscope and point it at nothing.
Thank you, Rick. So just to get started, Large Hadron Collider, if you're not familiar with it, it's a proton-proton, proton-ion, ion-ion collider. Design center mass is 14 TeV, so 1,000 times the CBAF energy. It's located at CERN near Geneva, Switzerland. Radius is 4.2 kilometers. The magnetic field is 8.5 Tesla, 11,000 amps to do that. First collisions were almost 10 years ago, and they're at 4 points. And the RF cavities are normal, and the magnets are superconducting, the exact opposite of the way CBAF runs things. So one of us is backwards. So why would you want such a thing? And the answer is to answer a question that goes back to the 19th century. How old is the Earth? And after the invention of thermodynamics in the middle of the 19th century, people were running into this crisis a few years later about how old the Earth could be. And you had, on one hand, the Helmholtzes of the world, and they argued that there's no way the sun could possibly shine for more than 10, 20 million years tops. So the Earth had to be about that old. And on the other, you had people looking down, the Darwins, Charles and George, and they argued that there are features on the Earth that are several hundred million years old, and the Earth could be no younger than its oldest feature. So there was a tension here. How is it going to be resolved? And here's where Helmholtz made a mistake. So what Helmholtz said is, let me relate the gravitational potential energy of the sun to its luminosity. And if you do this, you get numbers on the order of 10 million years. You can try and tweak this by having meteorites fall in, or in one case having the ether fall in, but it doesn't actually help you. You still get numbers that are this order of magnitude. And we know today that's not where the sun gets its energy. It comes from fusion. Turns out, though, this doesn't solve the problem. Right? If I add more energy to the system, it doesn't make the sun burn longer, it makes the sun burn brighter. If I throw a stick of dynamite in my fireplace, it doesn't make the fire burn longer. You could argue that, yes, now the fire will last as long as I own my house, but this is an issue of compressing duration, not anything else. So the sun is powered by this reaction. 4 protons go to a helium nucleus and 2 leptons, and this requires 2 protons to turn into 2 neutrons. That's the weak interaction, which is carried by the W boson. The strength of the interaction has a suppression of E over m to the 4th power, and for the sun, this is 10 to the minus 32. So this throttles the nuclear fusion rate, so the sun lasts for billions of years. Now you don't have this tension between looking up and looking down. So the reason the sun shines for billions of years is the W boson is heavy. Simple as that. If I change the W mass by 5%, it changes the sun's luminosity by a factor of 2. So it's a very strong function of this mass. But all this says is that, it's, if anyone has a 4-year-old going through why, this pushes the question one level of why back. If this happens because the W is heavy, why is the W heavy? And that's what the LHC is trying to find out. So let's step back to quantum mechanics. In quantum mechanics, the probability is given by the square of the wave function, and if I change this, the wave function to minus the wave function, there's no physical effects. A week later in the class, they tell you that you could actually write this as having a phase on top of the wave function. If I change the phase, it doesn't make any real difference, because when I change this phi, add this phase, when I add phi star, adds the opposite phase. Right now, if I can't actually observe this phase, how do I know it's the same over here as it is over there? How do I know it's the same today as it was yesterday? How do I, why does it have to be constant? And the answer is, well, it doesn't. The phase can be a function of space and time. This looks completely harmless, but it turns out this is a very, very powerful constraint on the kinds of theories you can write down. And here's the problem. It's one little derivative. Right? The Schrödinger equation and its descendants like the Dirac equation and so on, they have this derivative in there, and with 2 terms, the derivative of a product has 2 pieces to it. And that gives me leftover phi's. And at the end of the day, I can't have any. By construction, they're supposed to be unobservable. So if I want to write down a Lagrangian or Hamiltonian to describe electrically charged particles, I need to add a new piece to it, and that new piece is a massless photon. Right? Massless, a massive particle has 3 spin states, massive spin 1 particle, this way, or this way. However, if it's massless, it only has 2. And a hand-wavy way to think about this is, if it's massless, it's moving at the speed of light, so there's no way to overtake it, so the spin is pointing in another direction. So it's sort of hand-waving. To cancel the phi's, I need to add 2 and only 2 degrees of freedom. So this one and that one. If I add the middle states, that overdoes the cancellation, and I'm right back where I started. I have these unobservable phi's sitting everywhere. So the photon that I add must be massless. If you're serious, you want to think more technically, I need a parameter that has dimensions of mass, and there's no place I can put the mass in the Lagrangian that spoils the symmetry. Now, good theory is predictive, or at least retrodictive. So if I start with Coulomb's law and I want to make it work out with relativity in quantum mechanics, what pops out? Magnetism pops out, electromagnetic waves pops out, a quantum mechanical photon of 0 mass pops out, and experimentally the photon is massless. We know its mass is less than 10 to the minus 22 of an electron. Right? That's the concentrate. That's 10 molecules of ethanol in a glass of water. We call that light beer. It's roughly the radius of my head to the radius of the galaxy. And the third one, I used to put in probability, and I'd have the name of a particular celebrity or politician there. Won't do anything shameless or stupid in the next 12 months. That turns out to be less funny than it was in the past. So, let's do this again. So, if I describe electrically charged particles by Hamiltonian, out pops out a massless photon. I try to do the same thing with color charge, and out pops not just a massless gluon, but 8 massless gluons, the right number. And if I do this for the weak charge, I get massless W plus W minus and Z0 bosons, but experimentally they're heavy. So we're trying to figure out what breaks here, what makes the weak force different than all the other forces, what makes it weak. Alright, to do that we have to understand spontaneous symmetry breaking. This is the audience participation part. I've got 4 cities on the corners of a square, and I want to put train track between them so that you can get from any city to any other city. And I want to do that with the least track. So one option is to do this with 4 units of track. Alright, that costs me 4. I can do this with 3 as well, right? And I can get from that guy to that guy by going through the other 2. Alright, if you think this is optimal, put up your hand. Alright? Option 3. This requires 2 root 2. If you think this is optimal, put up your hand. Alright, I have 2 half hands. How many of you know the right answer, and how many of you just suspect a trap? Suspect a trap. Right. Exactly. Exactly. There's a trap. This is the real optimal solution. This actually takes only 1 plus root 3. And these are 120-degree angles, and I can get from any one to any other. So notice that the symmetry of the solution is lower than the symmetry of the problem. I had a problem with 4-fold symmetry, but the solution has only 2-fold symmetry. And if you're wondering how is this possible, there's another solution that goes the other way, and the sum of those two solutions still has the symmetry of the problem. This is spontaneous symmetry breaking. So you might have guessed the answer by looking at soap bubbles. Soap bubbles try to minimize their surface area, and they tend to go into this 120-degree. Same thing happens in a ferromagnet. Right? The Hamiltonian is spatially symmetric, but one direction gets pulled out of that, and everything aligns along that direction to get to the lowest energy state. If you're more mathematically inclined, if I have a coordinate potential, it can look like on the left hand, just have a lobe at the bottom, or it can have this wine bottle punt in the middle, and that is driven by this sign right there. This one has a solution right at the middle here where the symmetry is preserved. This one has a minimum over here, not at 0. The symmetry is spontaneously broken. This distance here, A, is called the VEV, the vacuum expectation value. That just means the value that minimizes it, which in this case is not 0. Alright, so what's the Higgs mechanism? I can write down a theory of massless weak bosons. There is nothing whatsoever wrong with this theory except that it doesn't describe the world we live in. I then add a doublet of spin-zero particles, and by doublet I mean 4. This is, again, bad terminology. It adds the particles and their antiparticles, and I can write down the interaction between the new doublet and itself, and the new doublet and the weak bosons in just the right way to do two things. First one is it spontaneously breaks the symmetry, just like a ferromagnet, and it allows something really cute to happen. The really cute thing is the massless W plus and phi plus that I just added mix. So instead of having 2 particles, I have 1 particle that has 3 spin states. That's a massive particle, so the W has gained a mass. The same thing happens for the W minus. The neutral case, it happens for one of the 2 combinations. That gives us the Z, and the other one doesn't couple to the Higgs field at all, and it gives the massless photon. So that gives you 1 degree of freedom left, and because of the non-zero VEV of the Higgs field, produces a massive Higgs. Now, how cute is it? It's pretty cute. That's my nephew. He can't help being this cute. It's genetic. So you really have very little choice in how you write down this theory. There's one free parameter, and that determines the Higgs boson's mass. There's one sign which determines whether the symmetry breaks or not. We saw that happen before. Other than that, it leaves the standard model pretty much untouched, except for adding a new Higgs boson, which we can then go out and look for. It also adds a new piece to the WW scattering cross-section. Otherwise, that would be infinite, which is another sign that a Higgsless theory is sick. And the new piece interferes destructively with the piece that was going to infinity and makes the whole thing nice and finite. In this model, the VEV of the Higgs field is the Fermi constant, give or take a square root factors of 2, and it shows a very deep connection between the weak interaction and the Higgs. So, our story so far. Unlike the photon and the gluon, W and Z are massive, an apparent violation of local gauge invariance and quantum mechanics. This is the thing that throttles nuclear fusion in the sun and lets it shine for 5 billion years. I fixed this as a Higgs mechanism, which is a spontaneously broken symmetry that allows the Higgs field to develop a non-zero vacuum expectation value that has dimensions of mass. And this allows the originally massless W to absorb a degree of freedom and become massive. Now, if this idea is right, and the vacuum really behaves this way, there will be a Higgs boson with predicted properties. Can we look at these things? And I've already screwed this up. Alright, so let's talk about how we look at these things in experiment design. The basic design of all of our experiments is the same, and this should look very familiar to most of you. We have a tracking chamber followed by electromagnetic and hadron calorimeters, which stop the particles and measure their energy, and finally a muon chamber to look at muons as they go through tracking, calorimetry, muons, and this is driven by the physics of the interaction of the particle with matter. Because the physics of the detection is the same, experiments all look more or less similar. So, for example, in a fixed target experiment, the beam comes, hits the target, and you have trackers, calorimeters, and muons, and again, different particles have different responses. This is an example of one such device. This is class. It stops at the red because of the physics that we're looking at. It makes no sense to build with the green and the blue on top of that. If you do a collider, you start with the same idea. Instead of having the beam come in, you're having a collision. Beam comes in the page, but you start with a fixed target detector like I had before. You replicate it, and then you keep replicating it until you've covered all the 4 pi. This is an example of what one of these detectors looks like. You have tracking, calorimeters, and finally a muon system, and each one of these basically you can think of as chopping and an area pointing to see what's happening at the interaction point. Atlas, the other experiment, has a very similar design, but it uses different technologies, and for good reason. Right? If you have a discovery of one of the experiments, you'd like to see it confirmed or refuted by another experiment that has very different technology, so you don't know that you're doing something wrong with how you built the experiment. Alright, so what do these detectors do? There's a plethosaurus of standard model measurements that cross over 12 orders of magnitude. We call these dinosaur plots because of their shape. And we have searches after searches after searches, and as of last month, each experiment had published about 350 search papers. In most cases, about 10 times the sensitivity of pre-LHC experiments. Some cases more, some cases less. I've decided that a death march through all 700 papers is probably not the right way to do this talk, so I'm not going to go into this in any detail. Instead, I'm going to talk about the Higgs boson discovery in 2012. Right, and depending on its mass, the decays are different. It wants to do, if it can, it wants to decay to heavy gauge bosons. That's its job. And if it can't, it wants to decay to fermions, the heaviest ones. That's its other job. Modes like gamma gamma, which we look at, are suppressed by a factor of about 1,000. So why would we want to do that? Well, although the signal is very small, the background is also very small and easy to understand. So while it looks like a crappy way to be looking at it, your background is much better than, say, glue glue, which although you're having 100 times the signal, you have 100,000 times as much background. Alright, so the best channels for the early searches are gamma gamma and ZZ. This is a typical 2-photon event, and by typical, we have graduate students staying up nights looking for events that look exactly this typical. It's hard to find an event that's quite this typical. Alright, you have tracks that are produced from the interaction point and 2 photons, one here, one there. You see their energies in the calorimeter. You see plenty of tracks, but none that are exactly pointing at that, particularly in 3 dimensions. It needs to hit within a millimeter or a few millimeters of the calorimeter to be considered a track. And one of the nice things about this particular detector is that the photons point back to the primary vertex. We have several collisions going on at any given time, so it's nice to be able to say that these 2 photons point at the same vertex. Alright, here's the data. You can see a bump there. That's the Higgs, but it's more fun. So, at the time of the discovery, the two experiments said we each see a particle with the same mass in two decay channels, about the same production rate, same two decay channels, same rate as the standard model Higgs, combined statistical significance above 6 sigma, less than 1 in a billion possibility of it being a fluctuation, and there was some minor supporting evidence. So, with more data, how does it look? This is the two-photon signature. To remind you, the Higgs bump is at 125, and you can watch as it kind of comes out of the background. That's when we switched energy. Luminosity went up, so it's going up faster, and now you can see the Higgs particle coming up. So not only is it persistent in the new data, and we've now collected much more data than this, it's coming at the right rates. So roughly for every collision, you have a certain probability of producing a Higgs. And there you go. So that's pretty clear. In the other channel, ZZ, again, 125 is the number you want to look at, so it's around there. All right, this is a much lower rate of study, so each event had a name as it came in, and people were looking at it. And the background looks particularly peculiar. These are 2Z events, and this is 1Z decaying to 4 leptons, and there's our Higgs over there. It helps when it comes in blue. So, what is our story so far? The vacuum is not perfectly symmetric. The Higgs field symmetry is broken. The vacuum expectation value is not zero. It's 246 GeV, which is the Fermi constant. And the weak decays are weak because the vacuum, more so than the weak force per se. You're actually seeing vacuum properties that make it weak. We know this because we can see the Higgs boson that the theory predicted pop out. So, in some ways, the vacuum is like a ferromagnet. There's a non-zero magnetization in the ground state of a ferromagnet. There's a non-zero vacuum expectation value of the Higgs in the vacuum. Unlike the ferromagnet, this 246 GeV doesn't point anywhere. It's a scalar. It's just a number. But there are other examples of condensed matter where you do get a scalar, and I've listed them there. Things like niobium, selenium, charged density wave superconductors, things I'm not very familiar with, but condensed matter physicists see this happening all the time, and they say, yes, this is exactly the same thing that's going on. Now, after we've seen the vacuum has one non-trivial property, does it have more? And Nima Arkani-Hamed always says, well, the Higgs is not telling us that. Now, the vacuum is not a crappy metal, although I think I've just shown you the vacuum is kind of a crappy metal. But it's also a crappy dielectric. Okay, trigger warning time. All right, those of you who've taken Jackson probably still live in fear of the Maxwell equations. The important thing about them is they're linear in the fields, and that means that light waves don't interact with each other, which is good. If they did, vision wouldn't be impossible because the light going here would screw up the light going there. In quantum mechanics, it's different. In quantum mechanics, this happens. The vacuum becomes polarized because I have a loop of particles, in this case electrons, running around in them, and that gives me an effective 4-photon interaction. So if I write down what the D and B fields look like, and I allow, this is what QED says they should be. So there's a linear piece you know, and then there are these nonlinear pieces. All right? The thing that matters for this is these last two here with the 7s in front of them, because they lead field components in different directions. That's what will allow light-by-light scattering. If you think of it classically, I've got light waves coming in, so the fields are pointing in a particular direction. When they scatter, they're now pointing in different directions. Well, how different could it be? You can write down the most general way of writing the D and E fields, and this is it. So you've got the piece that you remember from taking Jackson, and then you've got two other pieces here. This piece has the even Lorentz invariance times the same parity field. This one has the odd times the opposite parity field, and then they've got coefficients kappa and lambda in front of them. I just made up kappa and lambda. This is a post-Maxwellian parameterization formula for theories of EM. It's just empirical. But it's the most general expression you can write down, that it's Lorentz invariance, parity conserving, and the weakest new scale in field strength, which is cubic. Classical EM has these two coefficients at 0. QED has kappa of 2 and lambda of 7. Light-by-light scattering has sensitivity to lambda. Now, that was a toy model, a real model. This is a model of Born and Infeld. They had the problem of, why does the electron have the mass that it does and not infinite? Because if the electron is pointless, its field becomes infinite, field density becomes infinite, its mass becomes infinite. This is the problem. So they said, perhaps this is Lagrangian, and beta here is a free parameter with dimensions of mass squared. If it's infinity, you get the standard model. And what they're trying to do is they're saying, well, maybe there's an upper field strength limit. Once I get above 10 to the 20 or so volts per meter, perhaps fields no longer add linearly, and that keeps the electron mass finite. That's what they're trying to do. The same thing happens in string theories for the same reason. You're trying not to have infinities, so you impose these kinds of cutoffs. So, how do you explore these high electric fields? Turns out, lead is what you want. Lead 208, which is what they run at the accelerator. Lead 208 is more expensive than the gold they run at RIC, because it's isotopically pure. It has a radius of about 7 Fermi, so it has a surface field of about 2 times 10 to the 1 volts per meter. If I accelerate it to 5 TeV, it Lorentz contracts. It gets an aspect ratio about the same as a sheet of paper. And more importantly, the electric field around it also Lorentz transforms, so it becomes stronger by a factor of gamma, so I have fields of about 3 times 10 to the 25th volts per meter presence. There are similar measurements of people who are trying to explore nonlinear QED this way. Nobody, including this measurement, has seen it in its purest form. 2 photons in, 2 photons out. We're all looking at it somewhat indirectly. What this measurement is we look at these lead collisions where I've got field strengths greater than 10 to the 25th. The fields from the nuclei can be approximated as virtual photons. This is the Weizsäcker-Williams approximation. And the way to think about it is, if I'm watching the beam come by, if it's on this side, as it gets close to me, its field gets large and points in this direction. As it passes me, the field points in that direction. So what the field is doing is this, and that looks a lot like a photon. So the signal is 2 real photons in an otherwise empty event. The lead nucleus, in fact, usually survives this. Right, goes through intact. There's that little energy taken out of it, and we expect about a dozen events. So the signal is 2 back-to-back photons and nothing else in the events. Photon 1, photon 2, empty events. This is perspective. So they're actually back-to-back in phi, but they're pointing in that direction in eta. That is in forward. So it's a boosted system. This is what the background looks like. So it's simply a question of pulling this out of that. Now, not every event is signal. Atlas sees 13 events over a background of a little less than 3. I have the backgrounds all listed here for those of you who are interested in them. This is the one that's the killer, the central exclusive gamma-gamma. These are cases where I have 2 photons and nothing else in the event that had nothing to do with light-by-light scattering. Now, the good news is this is down an order of magnitude from the signal that we want, but, to be honest, how many of you are convinced by the background calculation? You'd like to see some evidence that this is a signal. And the thing that does that is the back-to-back cut, to require that the 2 photons be within 1.8 degrees of each other back-to-back. The reason this works is the signal source, I told you, was the electric field from the ion. Right? The background is caused by gluons that are sitting inside a nucleon inside the nucleus interact. Those gluons have motion inside the nucleon. The nucleon has Fermi motion inside of the ion, so it's moving around in all sorts of directions. So only in the rare cases it's back-to-back, and you can see this on this plot. So my signal in the red is almost all on this side of the selection requirement. My background in gray is pretty much flat and goes on everywhere. So the fact that we see out here a big signal in exactly the right angular distribution gives us confidence that we really are seeing light-by-light scattering. If you look at the diphoton mass, it's more or less what you expect. I'm going to keep turning this off. All right, so I have many event displays of this. I've looked at all 13 of them. We've shown you the top event before. The bottom also looks back to back. I could show you 11 other events that look exactly like this. Now, if you get to a cross-section, you have a number of systematic uncertainties, which add up to about 25%. If you have 13 events, you're talking about a statistical uncertainty between 1/3 and 1/4, again about 25%. We can go through all of this. We get a number of 70 nanobarns with that sort of uncertainty. Theoretical prediction is 50, again, well within that uncertainty. So, what have we learned through this detour about looking at light-by-light scattering? Well, the vacuum is polarizable, just like the crappy dielectric, but it takes enormous fields to do this, more than 10 to the 25th volts per meter. The degree of nonlinearity matches QED's prediction. If you go through the math, there's 9 plus or minus 3 is the measurement of lambda. QED predicts 7. Born-in-file type models are excluded for beta less than about 10 to the 4 GeV squared. It also tells us that the particle with the largest charge to mass ratio is the electron. And we didn't actually know that before. There are no mega-charged particles with very high mass. There's no particle of 1 GeV mass with 10 to the 12th charge. We know that now from experiment. I have no idea why anybody would propose such a thing, but at the point now is it's moot. There aren't anything out there like that. But this is different than most searches. Most searches are sensitive to mass. This is sensitive to charge over mass. So there are different things that you can see. Finally, in high school physics lab, I measured E over M for the electron to about 15%. Now, many years later, third of a century, $10 billion later, I measured E over M for the electron to about 15%. So I'm sure there's a lesson in that somewhere. All right, back to the Higgs. What have we learned? One thing that we learned is that there are exactly 3 fermion generations. There's the one that makes up the matter that we all know and love, or not. Right? There's the charm strange and muon and its neutrino, top atom, tau and its neutrino, and that's it. There's nothing else at all the way up to the Planck scale that replicates this. Second thing, nature has provided us a fundamental scalar, and as far as we can tell, its property matches the Higgs. Its mass makes no sense, and I'll explain why in a minute. And finally, the Higgs mass is suggesting that there's new physics at the TeV scale. And Flavor, however, is telling us that if it's there at all, it's at least 10 times heavier. So let's go with the argument for 3 generations. This is also a statement about the vacuum. The way you produce 90% of the Higgs is through this diagram. 2 photons come in, they interact with a virtual top loop in the vacuum, and pop out a Higgs. So they excite the vacuum through its TT bar properties, and out comes a real Higgs. Right? As in most times when you write down this kind of diagram, these kind of loops, right, the heavier the mass of the particle in the loop, the more suppressed the diagram is in the rear of the process. It doesn't happen in this case. This case is special. Because the Higgs couples to mass, the heavier the particle is, the stronger that coupling. And it turns out those two exactly cancel. So if there's a d prime and a t prime, right, I would have 3 times as many loops, and thus I would have 9 times the cross-section. Because it's a constant. So we are asked to determine whether our data fits this model or that model. That's 3, that's 4. So this is not a tiny effect. This is enormous. Right? One silly way to look at this is the number of generations is 3.00 plus or minus 0.04. 4 is excluded at very high confidence. Right? Another is that we're actually more confident that there are 3 families that the Higgs exists. Because we are more confident that the data excludes this point than excludes that point. So we're absolutely sure there are 3 and only 3 generations. Modulo loopholes. So there are loopholes. I'm talking about a truly sequential 3rd generation that gets its mass from the same Higgs that gives mass to the W's and Z's. If I have a more complicated theory where, example, the quarks are vector-like, there are multiple Higgs bosons, whatever, things can be different. You can also have always the miraculous cancellation. There are 2 pieces of new physics, one that turns it on and one that makes it look like it's not there. So there are loopholes, but insofar as you don't go through these loopholes, we know there are exactly 3 generations. You also might ask, well, how do you really know this is the Higgs? You found a scalar, but maybe it's something else. Well, this particle couples very strongly to ZZ, despite being 25 partial widths away from the pole. So the Higgs decays to 2Z, one can be on shell, but the other is stuck to being 40 GeV or less. And that's a huge degree from the pole. It also couples very strongly to W star. The equivalent figure is just unreadable. So no matter what, you can't write down a theory of electric symmetry breaking that does not include this new particle that has any hope of being right. So it looks exactly like a Higgs, and it definitely plays some role. Now, I mentioned, as far as we can tell, the Higgs couplings match what the standard model expects. And this is a clever way of putting different particles on the same curve. This is what you expect relative to the Higgs coupling, so that this line is at 1. And you think this is good news? And the answer is, well, maybe. The experimental sensitivity of the LHC is given by the red curve. And you can see everything is just above that sensitivity. So if things were well below the Higgs coupling, we wouldn't have seen the particles at all, and we wouldn't be on the plot. And if it was well above that, it would have been discovered much earlier at the Sevotron. So yes, it tells us something the couplings appear to be right, but perhaps not everything that you might want. This is everything you know about the Higgs in the first 2 generations. It all fits on one slide. What about another Higgs? Nature gave us 1, why not 2, or 10, or 100? One useful framework is to think about this is what's called the 2 Higgs doublet model. I added 1 doublet to give mass to the W's and Z's. Well, maybe that's not what happens. Maybe there's 2. And maybe there's 10, but let's think about just the first 2. If I add 1 more complex doublet, there's 4 degrees of freedom. That gives me 5 physical particles. A Higgs, another Higgs that looks more or less like it, a CP odd Higgs, and 2 charged Higgs. And you can put these models together in many different ways. You can say one Higgs deals with the up-type quarks and the other with the down-type. You can say one deals with the fermions, one deals with the bosons. You can say one operates on leptons, one on quarks, and so on. In type 2, which is SUSY-like, and I'll explain supersymmetry in a bit, there are two parameters. One is called alpha, that's mixing, how much of one Higgs is in the other, and beta, which is the ratio of the U-type VeV to the D-type VeV. People explain this with words that I don't understand, like superpotential and holomorphic. This is just how it works. There's two ways you can see this. One is direct observation. You just look and you discover a new particle. The other is by saying, the Higgs that we found at 125 has properties that are different from the standard model Higgs. And these two are coupled. If my other guy looks a lot like a standard model Higgs, it's easy to spot. If it looks very different, it might be hard. All right, some random facts, starting with humans share 50% of their DNA with bananas. Under supersymmetry, I'll get to that in a second, the Higgs mass is less than the Z mass all the time, which implies, right, because there's a cosine there. It could be that radiative corrections are large, or it could be we found the wrong Higgs, and we found the heavier guy, and I'll show you why this is not likely in a moment. The direct searches are just repeats of the original searches. At this moment, we have 15 times the data, which gives us about 4 times the sensitivity, but it only gives us 4 times the sensitivity. It doesn't give us 1,000 times sensitivity. And that's for a second Higgs that looks exactly like the first Higgs, right? If I'm mixing two different Higgses, the more one looks like the standard model, the less the other one does. And we're looking for the guy that doesn't look very much like the standard model. And experiments can really only measure a few things. One is topology. Was this produced with a W or extra jets? I can measure cross-sections, I can measure rates, and I can look at kinematics, energies, and angles. And in general, right, these are easier to measure, harder to measure, and they become less constraining as you go on down. So, in a 2 Higgs doublet model, the